In the last video, we learned about quantum numbers and how the electron clouds are arranged around an atom. Electron configuration will show you how the electrons are distributed in the atom. It describes electrons' location around the nucleus. I'm going to teach you two ways to write the electron configuration. This is step one. This step I think is a lot harder. You have to make sure everything is in order versus the second way in which I'll use the periodic table. In the previous video, we learned that the principal quantum number is represented by n, and it is equal to the energy level or the energy shells. Currently, there are 7, and they match the periods of the periodic table. If we discover more atoms, it could go up to infinity. So when n is equal to 1, you know we are at energy level 1. L, which is the angular momentum quantum number, gives you the shape of the orbital. So L is defined as n minus 1. So when n is equal to 1, 1 minus 1 is equal to 0. And we know 0 has a value of s. We also learned that m subscript L is the magnetic quantum number, and this gives you the orbitals. It is plus or minus L, and remember the orbitals are the electron clouds. So when it is plus or minus 0, the only possible is 0. So the electron cloud for L is equal to 0 is an S. The shape of an S is a sphere. If I rotate the sphere in space, the only possible orientation there is 1. It is 1s. So energy level 1 can only have an S. We also learned that each orbital can have a maximum of 2 electrons. So this is 1s2. When we are at energy level 2, L can be 0 or 1, because n minus 1 is 2 minus 1, and 2 minus 1 is a 1. In order to have a 1, we must have a 0 first. We stated 0 is an S. 1 is labeled as a P. So the shape of a 1 is a P, and it looks like a dumbbell. So when we do the orbital or the electron cloud here, it's a plus or minus L, which is 1. And remember we said it's arranged, so it's plus 1, 0, and 1. So there are 3 possible orbitals. Each orbital can have a maximum of 2 electrons. So 2 times 3 is 6. So this is why it's 2p6. Energy level 3, L, can be 0, 1, and 2. Why? Because if I look at L is equal to n minus 1, this is 3 minus 1, which equals 2. In order to have a 2, I must have a 1, and I must have a 0. We know 0 is an S, a 1 is a P. When L is equal to 2, the shape of the orbital is a D. If I find the number of orbitals, it is plus or minus 2. So the range is plus 2, plus 1, 0, minus 1, minus 2, which gives you 5. So 5 orbitals can hold a maximum of 10 electrons. When n is equal to 4, the possible values of L are 0, 1, 2, and 3. 0 represents S, 1 represents P, 2 represents D, and when L is equal to 3, the shape of the orbital is an F. And so if I find the magnetic quantum number, it's a plus or minus 3, so it's plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3, which gives you 7. So 7 times 2 is 14 maximum electrons. When n is equal to 5, the values for L possible are going to be 0, 1, 2, 3, and 4. It's going to be 0, 1, 2, 3, and 4. Because L is n minus 1, so 5 minus 1 is 4. And remember, in order to have The subshell 4, we must have a 3, we must have a 2, 1, and 0. 0 has the shape of an S, 1 has a shape of a P, 2 has a shape of a D, 3 has a shape of an F, 4 has a shape of a G, so this is 5G. To find the orbitals, we do ML, which is plus or minus 4. So plus 4, plus 3, plus 2, plus 1, 0. Minus 1, minus 2, minus 3, minus 4 will give you 9 orbitals. 9 times 2 will give you 18 electrons. So if we move on to 6, we're going to have 6G18. But since it's 6, we're going to also have a 5. 5 will be represented by H, so that's 6H. The number of orbital is plus or minus 5, so it's going to be 11. So there's going to be 22 electrons. And same goes for 7. So when you have energy level 7, you're going to have an L value of I. So if you notice, the orbitals increase by odd numbers, or you could add 2 each time. So that tells you in energy level 1, we can have a maximum of only 2 electrons. In energy level 2, we can have a maximum of 8 electrons because we have 2 from the S, 6 from the P. In energy level 3, we can have a maximum of 18 electrons because there's 2 from the S, 6 from the P, 10 from the D. And the fourth energy level, we have 32 because there's 2, and there's 6, 10, and 14, which equals 32. In the fifth energy level, we can have more than 32 because we have more orbitals. But we just state 32 because we have not discovered atoms that exist beyond F. So these numbers and the shapes will change once we discover more atoms. So in the previous video, when I gave you 2, 8, 18, 32, 32, 32, 32, this is why we have those numbers for each of the energy levels. So this table is arranged by energy levels and sub-energy levels. When we fill up the electrons, we always want to go from the ground state up. When an electron is located at a higher energy level, it is unstable, so it doesn't want to stay there. So we want to make the atom as stable as possible by filling from the lowest energy first and then going to the higher energy. We always go from right to left. So if I go right to left, the lowest energy possible is 1s2. So we fill up 1s2, and then we move to the next row, which is 2s2. So my lowest energy level is 1s2, followed by 2s2. And then again, we go back, and the next lowest energy level is 2p6, and then 3s2. And then we go to the next one, which is 3p6, followed by 4s2 right here. And again, we go to the right. We start from the right, and then we fill 3d10, 4p6, and then 5s2. If you notice, we stated that energy level 3 is lower than energy level 4. But if we look right here, we have 3p6, and then we go and fill 4s2 before we fill up 3d10. The reason we fill up 4s2 than 3d10 is 4s2 has a slightly lower energy than 3d10. Because these electron clouds are not isolated but overlapping, 4s2 is slightly lower than 3d10. And if you continue the pattern after 5s2, you go back to the right, 4d10 fills first before 5p6. So that means 5s2 is a little bit lower or slightly lower than 4d10. Then it's 5p6, 6s2, and again we go to the right and we fill 4f14, 5d10, 6p6, 7s2, and then we're going to go up again, 5f14, 6d10, 7p6, then 6f14, 7d10, and then 7f14. This is method 1 to show how electrons fill in an atom. The second method of filling the atom's electron is a lot easier because the periodic table is already arranged into blocks. We said the shapes of the orbitals were s, p, d, f. We also stated s can have 2 electrons, p can have 6 electrons, d can have 10 electrons, and F could have 14 electrons. In general, the periods of the periodic table matches the energy level. Period 1 is energy level 1, period 2 is 2, 3 is 3, 4, 5, 6, 7. The first time we see the S block is energy level 1. The lowest energy level is 1s2. Everything in the alkali metal, including hydrogen, is at S1. So that means hydrogen, and so for all of these are S1s. Everything in the alkaline earth metal, which is group 2, is at S2. So every element in column 2 is at S2. The only one exception is helium. Helium is also a S2. However, is located in the noble gas because it has properties of noble gas. Groups 13 to 18, starting with the boron family, is the p blocks. Remember, we could have 6 electrons. So in the p block, boron family is p1. So everything in boron family is a p1. Carbon family is p2. So everything in carbon family is p2. Nitrogen family is P3, oxygen family is P4, halogen family is P5, the noble gas is P6, but the noble gas will not start with helium because helium is S2 because it only has 2 electrons. We'll start with neon. So neon and below will all be P6. So the first time we see the P's are energy level 2. So this is energy level 2. Again, it matches the periods of the periodic table. This is 3, 4, 5, 6, and 7. The transition metals are the D blocks. Remember, these can have 10 electrons. So this is D1. So everything in this family is D1. This is D2, D3, D4, D5, D6, D7, D8, D9, D10. The first time you see the D blocks is energy level 3. This, even though it is period 4, the D blocks will be off by 1. So this will be 3D. The next row will be 4D, again off by 1 period. The 6th period will be the 5th D block, and the 7th will be the 6th D block. The rare earth elements, the 2 rows that are pulled out of your periodic table, is the F block. F can have 14 electrons. So everything here, this is F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F12, F13, F14. The first time you see the F block is energy level 4. And so the first row is energy level 4. The second row is energy level 5. Remember, these 2 rows are pulled out. This row appears here, and this row appears here. So if you notice, the 4F is off by 2, and the 5F is off by 2 from the periods. So how do we use this table? Let's say we are looking for the electron configuration of phosphorus. This is the location of phosphorus on your periodic table. Every shape SPDF will be filled except for the last orbital in the highest energy level. So we start with row 1. Everything in row 1 has to be filled because phosphorus has 15 electrons. So the lowest energy is going to be 1s2. Now I move down to the second row. The second row, we start with 2s2. It has to be completely filled. After 2s2, we go to here, which is 2p6. It still has to be completely filled because that's only 10 electron and phosphorus needs 15. So then we go to the next row. 3s2 is completely filled because we need both of those electrons. The next lowest energy level is 3p. 3p, where phosphorus is only p3, so it's 3p3. So all the energies are from low to high. We go in order. We go from left to right. Subshell, or the shape SPDF, is completely filled. We go to 2s, p6, d10, and f14. So let's do another one. Yttrium is right here on your periodic table. Again, we're going to start with the lowest energy level, which is 1. And we know all of 1s2 is filled because we need to go to 4d. The next row is 2s2, followed by 2p6. The next row is 3s2, followed by 3p6. After we finish 3p6, we are here. We go to the next row, which is 4s2. After 4s2, we are right here. This is 3d10 because the first time we see the D's are energy level 3. 4s2 is lower than 3d10 because of overlapping. After the end of d10, we're back to 4p6. We're right here now. We're going to go to the next row, which is 5s2. And after 5s2, we're right here where we're at yttrium right before. And this is 4d1 because yttrium is in d1. So this is the electron configuration of yttrium. You go from period 1 and in order. We always go from left to right. If the sub-energy level or sub-energy shell, which is the shapes or SPDF, is full, then we are always here. S2, P6, D10, F14. Let's do another example. The examples can be right here. This is element dy or diasporium. So we're going to start with the top row again. All of it fills, so it's 1s2. We are in the next row, which is right here. So it's 2s2 is completely filled. Then we are still in row 2, which is 2p6. So after energy level 2, we are at energy level 3, which is right here. We're going to fill all of 3s2. We're going to go to the right. We're going to be at 3p6. All of that's going to be filled. Then we come to the next row, which is period 4. All of period 4 is filled. So 4s2. And then it's 3d10 because these first appear in energy level 3. So it's off by 1. Then we go back to the p blocks, which is 4p6. After period 4, we're going to go to period 5. All of period 5 is going to be filled. So that's going to be 5s2. The s blocks are filled. Then followed by 4d10 and then 5p6. We're always going from left to right to fill. After the 5th period, we're at period 6 right here. 6s2 is filled. Right here, the lanthanide series right here goes right here. So after 6s2, we're going to go to 4f and it's going to go to 10. So due to overlapping, 4f has a lower energy than 5d. For most of the elements that are down here, the rare earth, it does not follow the order on the periodic table because the energy levels and the sub-energy level are so close to each other that sometimes 5D will fill partially and then 4F. Sometimes it won't. It depends on the element. For this class, you only need to know the order based on lowest energy to highest energy level. I will not test you on the exceptions. Electrons fill following the three principles. The first one is the Aufbau principle, which is fill from the lowest to the highest energy level. Whether you use method 1 or 2, the order is always from lowest to highest. The second principle is called Hund's rule. Hund's rule states 1 electron per orbital. Orbital is the orientation in space. This is also the m subscript L value. It is also the lines or the boxes we learned in class before pairing. We always have 1 electron per orbital because we want to minimize electron repulsion. The last rule we follow is called the Pauli exclusionary principle, which states that no two electrons can have the same quantum number. So this is the N, L, M subscript L, and M subscript S in a given orbital. Because no two electrons can have the same quantum number, the electrons in the orbital must be paired in opposite direction. And this is why MS has two values. It could be a +1/2 or a -1/2. So write the electron configuration for the following: lithium, aluminum, and iron. So for lithium, lithium is located right here. This is Li. So we're going to fill from the lowest to the highest. So this is going to be 1s2. It's going to be completely filled. Then we go to the second row, and lithium is in period 2, S1. So it's 3 electrons. Aluminum is located right here. Aluminum, we're going to start with period 1. All of period 1 is filled, so 1s2. All of period 2 is filled, so we're going to go to the end. So this is 2s2. Remember our sub-energy level. S can have 2. 2p6. P's can have maximum of 6. Now we're at row 3, which is period 3 or energy level 3. This is 3s2, which is completely filled. Now we go to aluminum. Aluminum is in 3p1. Last highest energy level is going to be 3p1. Iron is located right here. So this is Fe. So we're going to start with 1s2. All of that's filled. We're going to go to the next row, which is energy level 2, which is 2s2, completely filled. Going from left to right, we are at 2p6, completely filled. We're going to go to the next row or period, which is 3. All of s2 is filled. Then we go across to 3p6. It's completely filled. So now we're going to go to period 4. All of 4s is filled. And now we are at 3d, and iron is located at 6. So it's 3d6. Again, the first time you see the D's are at period is at energy level 3. So the period and the energy for the d orbitals are off by 1. In general, writing the electron configuration or the entire electron configuration for elements like lithium or fluorine, it's really simple. However, when you get to elements like barium or radon or uranium, it takes a long time. So we have a short notation. That notation is called noble gas notation. We put the noble gas symbol in bracket. The noble gas in the bracket represents all the electron configuration up to that noble gas. After the bracket, we write the remaining electron configuration for that particular atom. First thing we do is we locate the atom on the periodic table. We move one period up locate the noble gas in that period. We write the symbol of the noble gas in bracket and then the remaining electron configuration after the noble gas. So here's an example. If we have boron's electron configuration is 1s2 again. We start with row 1, then we go to row 2, 2s2, and then 2p1 because boron is right here, which is period 2, and this is P1 because that's the P block. So if I want to find the noble gas notation, I locate boron. Boron is right here. I go up 1 period to the noble gas, which is helium. So helium is in bracket. When I write helium in bracket, helium's notation is 1s2. So to get to boron, we have to write 2s2, 2p1. Let's do another one. Silver. So if I write the long notation for silver, start with 1s2. Then we go to the second row. We fill all the second row, which is 2s2, 2p6. We are now at the third row. It's completely filled. So that's 3s2, 3p6. Then I go to the next row right here, which is 4s2 is filled. Then we are at the D blocks, which is 3d10. D's are off by 1. And then we go back to 4p6. Now we're at the next row, which is 5s2, 4d9, because silver is in 4 and this is d9. To find a noble gas notation, we locate silver. We go up 1 period, which is period 4. We find a noble gas, which is krypton. So we write krypton in bracket. Krypton is located in period 4 because in the P block, this is 2, 3, 4. Since it's completely filled, this is 4p6. So krypton is up to 4p6, which is here. This represents the core electron or the noble gas. And then we need to write everything after. So it's 5s2, 4d9. This is my noble gas notation or the shortcut. Pause the video, write the electron configuration and the noble gas notation for lead, calcium, and manganese, and then check your answer. So lead is located right here. That's going to be 1s2, 2s2, 2p6. Remember, everything is going to be filled until we reach the P block here because PB is located in the P block. Row 3 is going to be 3s2, 3p6. Row 4 or period 4 is going to be 4s2, then 3d10. 4p6. Period 5 is going to be completely filled. That's going to be 5s2. After 5s2, that is going to be 4d10 and then 5p6. And then we are at period 6, which is 6s2. And remember, this right here goes here. So that's going to be 4f14. The F's first appear during energy level 4. After 4f14, we're back to the D blocks, and the D blocks are off by 1, so that's going to be 5d10, and then this is going to be 6p2, because this is 2, 3, 4, 5, 6, and it's in P2. So this is the long notation. So if I want to do the noble gas notation, I'm going to find lead. I'm going to go up 1 period, go to the noble gas, which is xenon. So I put xenon in bracket. We know that xenon is going to be 5p6 because it's in the P block in period 5. We go all the way to 5p6. That is completely filled. That is xenon in noble gas notation. And then I need to write everything else after. So that's the noble gas notation for lead. Next one is calcium. Calcium is located right here. So we're going to do the long notation. So 1s2. Everything is going to be completely filled until we reach 4 s's because calcium is located at 4s. 2s2, 2p6. Row 3 or period 3 is completely filled. 3s2, 3p6. We are at period 4 and calcium is in the s2 block. So this is 4s2. So the noble gas notation, we're going to locate calcium, go up 1 period, find the noble gas, which is argon. I put argon in brackets, the noble gas in bracket, and if you look at argon, this is period 3p6. So everything here is going to cancel out, and so we're going to have 4s2. Next one is manganese. Manganese is located right here. So for the long notation, everything is going to be filled until we reach 3D, because this is 3, 4, 5, 6, 1s2, 2s2, 2p6. Period 3 is completely filled, 3s2, 3p6. We are at period 4. 4s2 is completely filled. And once we go to 3D, because the D's are off by 1, we go 1, 2, 3, 4, 5. That's D5. To do the noble gas notation, we locate manganese, and then I go 1 up and I find the noble gas, that is argon in bracket. Argon is located in period 3, P6. So all of that is covered by the bracket AR, and then we write 4s2, 3d5. Orbital diagrams or notation are visual representation of how atoms' electrons are distributed in energy levels. Electrons are represented by half arrows or full arrows. Orbitals are represented by boxes or lines. In general, I will be using lines. Remember, orbitals are the M subscript L's. These are the orientation in space. In the following examples, you're going to draw the orbital diagrams for the following atoms. In order to draw the orbital diagrams, we need to write the electron configuration. Magnesium is located right here. The electron configuration is 1s2, 2s2, 2p6, 3s2. So my orbital diagrams are going to be represented by a line. You can use boxes, it just takes longer to draw. Since these are orbital diagrams, we are doing orientations in space, or M subscript L. S has one orientation in space, so it's represented by one line or one box. 2s is also an S. There is only one orientation in space or one line. P, ML can be plus or minus 0, or plus 1, 0, minus 1. So there's 3 lines to represent the 3 orbitals in space. So this is 2p6. 3s, again, since it's an S, there is only one orbital in space, or 1 ml value. So when we fill orbital diagrams, we fill using the 3 principles that we learned in the previous slide. We use the all-buff principle, meaning that we fill the lowest energy level first. 1s2 is the lowest energy, so we must completely fill 1s2 before we could fill the next lowest energy level. So 1s2 is the lowest. Then I follow Hund's rule. Hund's rule states there are 1 electron per orbital. Since there's only 1 orbital, I put 1 electron, and then I go back and pair, but I pair upside down because Pauli exclusionary principle states that the electrons cannot have the same quantum number, so the spin has to be in the opposite direction. The next lowest energy level, according to all-buff principle, is 2s2. Since there is only 1 orbital, again, Hund's rule, 1 electron per orbital, I come back and fill upside down because Pauli states there must be an opposite spin. The next lowest energy level is 2p6, according to all-buff principle. Hund's rule states there's 1 electron per orbital. Since there are 3 orbitals, I put 1 electron in each orbital to minimize electron repulsion. Then I go back and pair them upside down using Pauli exclusionary principle. And I'm going to fill all 6 because I need 6 electrons here. The next lowest energy level is 3s2. So Hund's rule, 1 per orbital. And I pair upside down because I need 2. So this is the electron configuration and orbital diagram for magnesium. Pause the video, try B and C on your own, and then check your answer. So nitrogen is located right here. So first thing I'm going to do is write the electron configuration, which is 1s2, 2s2, 2p3. So S's have only one orbital or orientation in space. No matter what energy level, S's will only have one orientation in space, so one line. Same goes for P. Whether it is in energy level 2 or 7, it only has 3 orientations in space, or 3 values of M subscript L, so there's only 3 lines. So I'm going to use the Orbital principle, fill the lowest energy level first, which is 1s2. I'm going to follow Hund's rule, 1 per orbital. Pauli says upside down. I completely fill 1s2 before I move to the next one. The next lowest energy level is 2s2. Hund's rule states 1 per orbital. Pauli says they must be upside down so that no 2 electrons have the same quantum number. Next lowest energy level, according to above, is 2p. Hund's rule states 1 electron per orbital. 1, 1, 1. I only need 3. I am finished. This is not correct. This is incorrect. It violates Hund's rule. Bromine is located in the halogen. 1s2, 2s2, 2p6. 3s2, 3p6, 4s2, 3d10, and then 4p5. So 1s has one orbital, 2s has one orbital. All p's have 3 orbitals. 3s, since it's an s, has 1 orbital. 3p, again, since it's a p, it has 3 orbitals. 4s, since it's an s, has 1 orbital. D's have 5 orientation in space. The shape of D, or the value of L, is 2. So ML is equal to L, which is plus or minus 2. So plus 2 plus 1, 0, minus 1, minus 2. So there's 5. So every D orbitals have 5. And 4p will also have 3. So we're going to use Alpha, fill it 1s2 first, lowest energy first. Hund's rule states there's 1 electron per orbital. Pauli upside down. Alpha principle 2s. Hund's 1 per orbital. Pauli upside down. Next lowest energy level is 2p6, 1 per orbital. 1, 2, 3. Pauli 1, 2, 3. Because I need 6. Next lowest energy level is 3s2 above. Hund's 1 per orbital. Pauli upside down. Next lowest is 3p6. Hund's 1, 2, 3. Pauli 4, 5, 6. I need 6 here. Next is 4s. Hund's 1 per orbital. Pauli's upside down. I need 10 in the 3D. Hund's states 1 per orbital. 1, 2, 3, 4, 5. They all go in the same direction. Pauli says I need to pair them upside down, and I need 10 of them total. So they're completely filled. The last energy level, which is 4p5, Hund's rule, 1, 2, 3. I come back and pair 1, 2. So I'm done. If we have one orbital that has only 1 electron. So when we do orbital diagrams or any electron configuration, we follow the 3 principle. Aufbau principle states we fill the lowest energy level first completely before we move on to the next energy level. Hund states we can only have 1 electron per orbital to minimize electron repulsion. Remember, orbitals are M subscript L. These are the orientation in space. All S's have 1 orientation. All P's have 3. All D's have 5. All F's have 7. Pauli's exclusionary principle states that the electrons must be paired in opposite direction because no 2 electrons can have the same quantum set of numbers.